Well, last but not least, our final and eighth speaker is Professor Ana Claudia Arias from the University of California at Berkeley in the United States of America.
Ana Claudia will talk about power sources for flexible electronic devices. Welcome, Ana Claudia. If you want to share your screen.
Yes, thank you very much for this invitation. Like many of you, I have been to many conferences where I was the only female speaker, and it's very nice to be here in this forum with all of you. And it's good to see old friends talking too. So today I'll talk about power sources for flexible electronics, which is a talk that I don't typically give because most people ask me to talk about the applications. So I'm happy twice to be here and have this opportunity to talk about this work. I have been working on this field of flexible electronics and different materials, I guess, unconventional materials for many years. My interest, I started with light emitting diodes and then solar cells. And in the past, I would say 15 years or so, I've been looking at flexible electronics with the view
Anna?
of...
I'm sorry, Anna, to interrupt you. We cannot see your screen. Can you share it for us, please? Perfect.
It worked? Okay.
Yes, we are there now. Thank you.
Okay, restart. Okay, so as I was saying, I have been working on flexible electronics, thinking about the whole system approach. So we look at materials that are not conventional. I have been working a lot on printing technologies because the printing technologies can be used as a deposition and a patterning technique. There's a lot of work on organic electronics, especially optoelectronics, that we have been developing with the idea of, since I am not a chemist, I try to work with materials that have shown reliable performance. And by reliable, I mean that I can process in there, I can print, and I know that I'll get a performance that is good for the device. So not trying to push the records on efficiency or luminescence, but really trying to have reliable performance under the printing conditions that we work on. We try to demonstrate this technology in systems, because in systems and applications, you will find the bottlenecks and find what's important, what matters for the performance of the system, and what perhaps you're ignoring and not paying attention when you put all these materials together and you start integrating different materials. We have been developing hybrid approaches also because for some of the devices, especially wireless devices, communications is important, and the printed electronics is really not good enough for communications. So the printing aspects, it's something that I like a lot because it allows you to study the materials and how the morphology and how the materials will interact with different surfaces in a very nice controlled way, where you'll have small quantities of materials that are deposited in the substrate as opposed to spin coating. Of course, as a green technology, let's say, you do move away from wasting a lot of materials with the conventional subtractive processes, and now you deposit the material that you want in the area that you need that functionality, and there is no subtraction. And there's a lot of interesting problems that you work when you have these little droplets or puddles in some cases interacting with the surface and with the materials that have been previously deposited. There was a question for Daria before on the printing techniques. Indeed, there are so many printing techniques that one could use to deposit these materials that we work with. The criteria is ultimately in the film properties that you want to achieve. Of course, we want a low roughness. We want to control the film thickness very carefully, since the film thickness has a direct impact on the performance of the device that you're fabricating. The line width is important because it defines our critical features, since now we are not using photolithography to define these features or evaporation. And of course, if you want to work on large area or have arrays of devices that help the reproducibility of the system, large area scalability is also important. So we pick and choose depending on the ink, depending on the viscosity, and depending on the coverage that we want to achieve on the substrate for that particular material. There is no, I don't believe that there is one technique that can do the job for every material that we use in electronic devices. For solar cells, for example, we like to use blade coating for PDOT and for the organic layers, but we like to use a screen printing for the wires, since then you can get much thicker films. While for photodiodes, for example, we only use blade coating or inkjet printing, because then we can live with a thinner connectors in that case. While the solar cells, higher currents, you want to have thicker wires. So mix and match. I will not talk about the printing techniques so much. So the group has been working on, as I said, applications and systems. A lot of applications are in large area, where we look at image sensors, solar cells, and a lot of photodiode arrays. We have worked in medical devices, medical applications, especially using some of the optoelectronics in medical devices. And today I'll talk about the power sources. For the medical devices, I have to say that when you start mixing printing techniques with flexible materials for devices that are going to be on the body, we have shown that these printed devices and these flexible devices outperform all the alternatives that are today available to us. So we have shown these devices applied to MRI, magnetic resonance imaging, and we see that a much higher SNR as compared to the devices that we have in the hospital. We have compared with blood oximeters and just vital sign monitoring in general. And again, the signal to noise ratio is incredibly higher than what you get in the commercial devices, and also in some devices to monitor the formation of blood ulcers in the skin. So I am convinced that all these materials and devices and interfaces that we study will play an important role in many applications, including applications with the impact of a medical device. But what keeps us going to work every day, of course, is fun. And when you start mixing materials and patterning techniques, and you look at electronic devices in from the design point of view, we are no longer attached to the components that we want to buy in a catalog. So we can design electronics that are completely different and customized for the need of that system. And really moving from this one size fits all electronics looking square in a black box to something that looks different, has different colors, different feel, and performs just as well, if not better, than what we have available. So in terms of powers for flexible systems, we have looked at the system of the power itself, where you would want some sort of energy harvesting. We looked at several mechanisms for energy harvesting and concluded that a solar cell is the most effective that we could get for the systems that we were looking at, in combination with a battery. And of course, then you also have to think about the power electronics, because you are introducing these power sources in an electronic device, and you want your power delivery to be constant and to be reliable, and you don't want variations in the power, the levels of current and the levels of voltage that you get. For that, you do need power electronics. So we looked into how to have all these three components, harvesting, storage, and power electronics in a flexible format. And the conclusion is that of course, for all electronic devices, especially autonomous devices, you need it to be reliable. So you do need a combination of harvesting and storage. You do want to be wireless, and wireless can be understood in two ways. It can be wireless communication. So if you're collecting data and you want to communicate with the world, then you need wireless transmission, which then you will need a silicon chip. But some people also interpret as cableless, which is very important, because I guarantee you most papers that we see on flexible electronics actually have all sorts of cables and huge boxes that are making that device work. So we try to have a device that looks like a piece of paper like this. This is a bio, but that is completely cableless, and it has all the components in that flexible substrate. Of course, it has to be efficient. We will not be successful if our performance is lower than what industry and consumers want. And we have to look at the load. Sometimes when we are characterizing devices in isolation, we are concerned about the figure of merit of that device, and that helps materials development. But when we take that device and put in a system, then you have to look at what's the loads that that device is going to be connected to. And that's where the power electronics comes in play. And of course, we try to have printed and flexible whenever possible. So I'll show you two examples of systems that we have looked and designed the power box, which is not a box, the power sheet for a system, a flexible system. Over the years, my group has worked in two formats for the batteries. One format is what we call the pillow format, where you deposit layers on top of each other, and then you seal it with some sort of flexible metal foil. and you come with this squishy pillow. As you saw before, batteries always have an electrolyte, so you have to seal so it doesn't dry, and it's like a cushy pillow. You can fold, you can play with it, and you get reliable output. We have also worked with batteries that have a wire format, and this comes from the realization that most of our electronic devices have wires. We wear things that have the shape or could have the shape of a wire. So when we looked at flexible power sources, maybe a wire itself, it wouldn't be a bad format or a bad form factor for a battery. So this black wire that you see here is actually a battery, where the current collector is a zinc filament, and then we wrap the other current collector and the separator and the electrolyte all in this along this wire. And you can see that this wire can power LEDs, just like this pillow shape can also power the LED. So my student here, Ala Zaramaeva, a very fashionable person and determined to make electronics beautiful, got together with Emily Osterfeld, who passionate about solar cells. And this is the result of their collaboration. For this system, what they wanted to show was that we could wear a power source or a device that could power our devices and harvest the light from the sun, and have something that we actually would want to wear. So here, the requirements of the systems was we wanted a power source and that would give us a voltage range of 1.5 and 1.8, and a power between 25 microwatts and 5 milliwatts. And that should be enough for some of the wearable electronics accessory. So this is what you see here, the PV module that was done on glass to get better reliability than flexible. And here's our wire battery. I have gotten requests for buying such a thing due to our paper. We are not selling them, but okay. So the solar module, it was 4 solar cells connected, and you can see here the performance of 1 solar cell versus the performance of 4 solar cells. The reason to have these solar cells connected was to get a higher voltage, and voltage that is somewhat compatible with the battery that we were using. We characterize these solar cells under the sunlight, also under indoor lighting. For many reasons, organics actually outperform silicon indoors. So we do characterize our solar cells when we have just indoor light. And here you can see, of course, your light source and your light intensity plays a role in the output current if you are using the solar cells connected with your load. The purpose of the solar cell, this bracelet, was to charge the battery. We see here that if you are in the sun, in the Californian sun, you can charge this battery in a couple of hours. And here's just showing that you get to full voltage and the currents that you expect in a couple of hours. And then these 2 students did an experiment where they were wearing these bracelets during the day. So here you see sunlight when they're coming to the lab, here when they're working in the lab, and then they go outside for lunch, and then work in the lab, and when they're walking home. And of course, they were collecting the data over many days. And here's just one snapshot to show that these organic solar cells, or this module that we developed, could be used to charge a zinc silver battery in indoor conditions and outdoor conditions. So just one example. The second example that I have here, we had a much more well-defined, better defined requirements, because we were working with Intel. And what Intel wanted was to have a battery that was flexible enough such that you could put the battery in the band of a wearable device like this one that I have. And they wanted it to, of course, you have a very specific output, but also lifetime and bending cycles was very important for them. We even got a prototype where we actually got batteries in the bands of these wearable devices. So for that, the voltage requirement was higher. So we had to change the chemistry of the battery, and that's when we went to lithium-ion batteries. And the power requirement was also higher than our little bracelets that we did for fun and for fashion. And the specific application that they want us to work on was a health monitoring device that would be in the shape of a wearable device. So in this case, we looked at a PV module that was commercially available, a morphosilicon flexible PV module, just because it was stable for longer in there than the devices we could make in the lab. And here you see the performance of this PV module with different irradiance. And what we wanted was a performance for this PV module here in the range where the battery is operating. So we characterize the battery lifetime without the PV module and with the PV module. And you see here that without the PV module, the lifetime of the battery would be about 6 hours, while if we had the PV module attached to this battery and just moved around the day and relied on the module recharging the battery, then it would last for 20 hours, which was what Intel in this case wanted. That's the lifetime had to be an hour under that format. So we were limited in area also. So then the pulse oximeter, which is one of the devices that we have worked a lot, had about 20 milliamps consumption when it's on. But you can turn the device on and off since it's a pulsating measurement. So that was our characterization of the battery here, when we have the load on and the load off being the load here, the pulse oximeter. There was a lot of work that we had. I see Monica, so I must be near my time. We had to do a lot of development on the device, on the materials themselves, and also on the packaging, because of the flexibility requirement. So we made our layers much thinner, and with that, we were able to make batteries that are very flexible, as you can see here. And the materials that we used are also posted here. So you see that we looked at binders and how to retain the flexibility of these thin films while not suffering in the capacity of the battery. So you see here that when we characterize the charge and discharge of these batteries over many charge-discharge cycles, we get very consistent performance. The Coulombic efficiency is near 100% over all these cycles. And then here you can see a typical curve for discharge and charge of the battery in cycle 1, 10, and 100, where you see that they're really on top of each other. We also looked at different, you see this is a very slow charge and discharge rate. We look at much faster charge and discharge rates because, especially for wireless devices, you would want the power to be delivered very quickly, and that's when supercapacitors become important. But we found that our batteries were sufficiently good for that application up to a charge rate of 3C. And here is just showing how the capacity then it starts decreasing when you go to very fast cycles. Flexibility was important. So here, what I'm showing you is our cycle and our charge and discharge cycles with flexing cycles in between. So every dotted dashed line that you see here, we turn off the battery and we flex for 200 times, and then we turn it on, characterize, flex 200, and so on. So you see here the comparison of cycle 3, which was flat, and cycle 17, which was flexed 600 times, and they again are on top of each other. So eventually, after quite a few years of efforts here, we were able to power a commercial pulse oximeter with these batteries, and then with the solar cell helping with the charging of the batteries. And here you can see the output of a blood oximeter, which we all have used now because of COVID-19. At different places in this discharge cycle of the battery.
Ana Claudia, can we?
Yes, I will stop here. So just by saying where we are going with this. We are now looking at how can we power devices in a more efficient way, knowing that our devices have changed a bit, even if you don't consider printing, they are becoming smaller and smaller, but the batteries are still ginormous and they are still the biggest part of our devices. So we have a project where we are trying to print a battery on the back of every silicon chip so that we can power the chip locally and try to reduce the load that is needed for the overall system. So I had some of the results from this here. I'll jump to thank my students who have done most of the work. Our battery guru is Ala here. And a lot of the work was done by Ala, and a lot of the system work was done by Yasser. And I also want to thank my collaborators from the Berkeley Wireless Research Center. And, you know, this is how we meet these days. And I will just stop here, leaving the generous people who have funded our work. Thank you so much for the opportunity here.
Ana Claudia, thank you very much for your talk. It was very, very interesting, especially for me that I used to work in batteries and now in solar cells. Unfortunately, we're running out of time because we want to go directly to the roundtable. So I will ask the audience if you have any questions for Ana Claudia, please direct her by email or let us know. We can direct the question to her. Thank you very much, Ana Claudia.